Good morning, class. Today we are going to discuss about an advanced material subject topic, that is the third of fourth unit, that is third unit, the relationship of compliance and stiffness matrix to engineering elastic constants of a lamina. Actually, the unit name is the macro mechanical analysis of lamina. So in that chapter, we are going to a new topic. We are going to discuss a new topic about relationship of compliance and stiffness and matrix to engineering elastic constants of lamina. Last class we are what topic we are discussed. Hooke's law for stiffness matrix from three-dimensional to two-dimensional. So today we are going to discuss about engineering elastic constants of a lamina. So the relationship of stress strain through the compliance S and reduction of stiffness Q matrices. See, S stiffness matrix and stiffness matrix X Q matrix X, S and Q, and reduction of reduced stiffness matrices. However, stress and strains are generally related through engineering elastic constants. For a unidirectional lamina, these engineering elastic constants are, for unidirectional lamina, the elastic engineering constants are, first one E1 is equal, and what is E2 is equal, and V12 and G12. So here E1 is equal longitudinal Young's modulus, longitudinal Young's modulus in direction 1. So same transverse Young's modulus, transverse Young's modulus in direction 2. So E1 is equal longitudinal Young's modulus in direction 1, and E2 is equal transverse Young's modulus in direction 2, and V12 is equal major Poisson's ratio. Major Poisson's ratio, where the general Poisson ratio is Vij is defined as the ratio of negative to the normal strain in direction J to the normal strain in direction I when the only normal load is applied in I direction. So next one G12 is in plane shear modulus. In plane shear modulus, that is plane 1, 2. So let us I will show some diagrams for you for understanding. See, this is the one type of material. So in that one plane 1 and 2. So there is longitudinal sigma x, and it is sigma 1 longitudinal direction at sigma 1 particular direction. This is one direction, and we need to calculate and one more direction, that is the second direction, normal sigma 2, and this one is also sigma 2, and 1 and 2, plane 1 and 2. So finally this is A and this is B, and finally C is this one is one direction, this shear stress. So tau 1 2, tau 1 2. So this is plane 1 and 2. See, these are the three directions. First one longitudinal, and the next one normal direction, and next one shear stress. Okay, shear stress produced at that particular section. So application of stresses to find engineering constants for unidirectional lamina. So experimentally, there are 4 independent engineering elastic constants are measured as follows. Apply a pure tensile load direction 1. So in direction 1, sigma 1 is not equal to 0, sigma 2 is equal to 0, and tau 1 2 is equal to 0. So in direction 1, sigma 1 is not equal to 0, sigma 2 is equal to 0, tau 1 2 is equal to 0. So from equation, we already discussed about already previous class some equations. Epsilon 1 is equal S11 sigma 1, epsilon 2 is equal S12 sigma 1, and gamma 1 2 is equal to 0. So these equations are getting from Hooke's law generalized equations. So already we have discussed and how we can get. So by definition of, if only the non-zero stress is sigma 1 is the case here. So non-zero stress. So here E1 is equal to sigma 1 by epsilon 1 by S 1 and V12 is equal to plane shear modulus E2 epsilon 1 by epsilon 1, that is equal to S12 by S11. So apply a pure tensile in direction 2. So these are all direction 1, and next one we can need to apply to direction 2. So in direction 2 we can get sigma 1 is equal to 0 at the same, sigma 2 is equal not equal to 0, and tau 1 2 is equal to 0. So from equation we can get epsilon 1 is equal S12 sigma 2. So epsilon 2 is equal S12 S22 sigma 2, and gamma 1 2 is equal to 0. So if only non-zero stress sigma 2 in this case, so here we can get non-zero stress sigma 1 by E1. So automatically here you can get E is equal to E2 is equal to sigma 2 by sigma 1 and sigma 2 and 1 by S22, and finally V21 is equal to sigma 1 by sigma 2. It is the ratio of stress to strain, and S12 by S22. Okay, so these are the equations you can get. So here V21 term is called minor Poisson ratio. So this V21 term is called minor Poisson's ratio. So finally we can get V12 by E1 is equal to V21 by E2. So apply a pure stress in the plane 1 2. Next, apply a pure stress at in plane 1 2. Plane 1 2. See, sigma 1 is equal to 0 and sigma 2 is equal to 0, and tau 1 is not equal to 0. So this is unidirectional for a laminar. This is the common for all in one particular any direction. So here from equation we can get sigma 1 is equal to 0, sigma 2 is equal to 0. So gamma 1 2 is equal to S66 tau 2 1 2. See, tau 1 2. So this equation you can get from stiffness matrix equation, generalized stiffness matrix equation. So thus we have provided S11 is equal 1 by E1, S12 is equal V12 by E1, S2 is equal 1 by E2. At the same time S66 is equal 1 by G12. So also the stiffness coefficients Q are related to engineering constant through equation. From above equations we can get finally Q11 is equal to E1 by 1 minus V21 V12. 1 2. So Q12 is equal V12 E2 divided by 1 minus V21 V12. So Q22 is equal to E2 by 1 minus V21 by V12. Finally Q66 is equal G12. So this is the equation, final equation where we get. So this is one particular direction, one direction, and this equation is second direction. So both directions are discussed about. We can find out finally Q66 and G12. So here the equations, there are the four equations you can get from stress strains through any of the following combinations. You can get Q11, Q12 and Q22, Q66 are S11, S12, S22, S66 are E1, E2, V12, G12. So these are the final equations of these are the relationship of compliance and stiffness matrix at the engineering elastic constants of a lambda. Next class we discussed about next topic. Thank you.